Last November I was reading through Nature, the scientific journal, and I came across a paper that made me stop mid-sentence and read the abstract thrice. Google DeepMind had just announced an AI system that predicted 380,000 new stable materials in months. To put that in perspective, that's more materials than every scientist, in every lab, in every country on Earth, had discovered in the last 800 years. Combined, I remember thinking, this can't be right. This has to be hype. This has to be oversimplified science journalism. So I downloaded the actual paper, all 47 pages, and I spent the next week reading it, looking up references, trying to understand if this was real. It's real, and it's just the beginning. Because right now, in a windowless laboratory in California, a robotic system is creating materials that have never existed. Not anywhere on Earth. Not anywhere in space. Not anywhere in the known universe. No human told it what to make. No human is supervising it. And in just 17 days of autonomous operation, it successfully synthesized 41 new materials from scratch. What's happening right now in materials science isn't an evolution. It's a detonation, and almost nobody outside the field knows it's happening. Before I show you what AI is doing, you need to understand why materials science is so fundamentally important. Every major leap in human civilization wasn't defined by an idea. It was defined by a material. We literally name entire eras of human history after the materials that defined them. The Stone Age, the Bronze Age, the Iron Age. We don't call it the thinking about Fire Age. We call it the Bronze Age because bronze changed what humans could build. And what they could build changed everything else. Look around you right now. Your phone exists because someone figured out how to purify silicon to 99.99999% purity SX9s of purity. The jet engine works because engineers developed nickel-based superalloys that can survive in gas temperatures exceeding 1,500 degrees Celsius while being actively cooled. The lithium-ion battery in your laptop was only possible after decades of research into specific cathode and anode materials with the right electrochemical properties. Materials aren't just components of technology. They are the technology, but here's the problem that has held humanity back for centuries. Discovering a new material is one of the slowest, most painful processes in science. This is the story of how AI is reinventing the physical world, one atom at a time. And why what I learned researching this changed how I think about the next 20 years of human civilization. Let me show you what materials discovery has looked like for most of human history. A researcher has a hypothesis. Maybe mixing element A with element B at a certain temperature will produce something with interesting properties. So they go into the lab. They carefully measure out precursor chemicals, sometimes spending days, just preparing a single sample. They mixed them. They heat them in a furnace. They wait, sometimes for hours, sometimes for days. Then they pull it out and characterize it. X-ray diffraction to determine crystal structure. Electron microscopy to see the microstructure. Mechanical testing, thermal analysis, electrical measurements. Each test can take days, 2 weeks. And after all that, after weeks or months of work on a single composition, the result is usually nothing useful. The material isn't stable. Or it's stable, but brittle. Or it's strong but impossible to manufacture at scale. Or it turns out it already exists and was discovered in 1987. Back to square one. This is how materials science has worked for centuries. Informed trial and error, educated guessing, and extraordinary patience. And some of the most important materials in history were discovered entirely by accident. Stainless steel was discovered in 1913 when Harry Burleigh was trying to make better gun barrels and noticed one sample didn't rust. Teflon was discovered in 1938 when a refrigerant experiment went wrong and left a slippery residue. Vulcanized rubber was discovered in 1839 when Charles Goodyear accidentally dropped rubber mixed with sulfur onto a hot stove. Breakthroughs came from serendipity, not strategy. And even when a promising material is discovered, getting it from the lab into the real world takes an agonizingly long time. The industry average is 10 to 20 years from discovery to commercial product. A material discovered today might not reach consumers until 2045. For centuries, this was the best we could do. Human intuition, human hands, human time. And then, in November 2023, everything changed. On November 29th, 2023, DeepMind published a paper in Nature that quietly detonated the entire field of materials science. The paper introduced an AI system called GNoME, Graph Networks for Materials Exploration. And what GNoME accomplished is one of the most staggering feats of scientific discovery in modern history. Before GNoME, humanity knew of approximately 48,000 stable inorganic crystal structures. GNoME predicted 2.2 million new crystal structures, and of those, 380,000 are predicted to be thermodynamically stable, meaning they could actually be synthesized. Before GNoME, 48,000 known stable materials. After GNoME, 428,000 known stable materials, an increase of nearly 800% in months. Let me put that in perspective. One AI system expanded humanity's catalog by nearly 8 times, the equivalent of roughly 800 years of human experimental discovery. When I first saw these numbers, I was skeptical. Predictions are easy, reality is hard. So, I looked for the validation, and that's where this gets truly remarkable. External researchers, not Google, independent lab selected materials from GNoME's predictions and attempted to synthesize them in real laboratories. Over 80% of the tested predictions were confirmed. The materials were real. They were stable. GNoME wasn't hallucinating. It was discovering. Now, how does GNoME actually work? Every material has a crystal structure, a specific three-dimensional arrangement of atoms. The way atoms are arranged determines everything: strength, electrical conductivity, transparency, magnetic properties, thermal stability. GNoME represents these crystal structures as mathematical graphs. Each atom becomes a node. Each chemical bond becomes an edge. The properties of each atom, its element, its charge, its local environment, become features attached to that node. Then GNoME feeds these graphs into a graph neural network, a type of AI designed to learn patterns from graph-structured data. GNoME was trained on hundreds of thousands of known crystal structures from databases like the Materials Project. Through that training, it learned the deep patterns of atomic stability, not the rules humans wrote in textbooks, the actual patterns, the subtle, high-dimensional relationships between atomic arrangements and thermodynamic stability. GNoME then used two approaches to discover new materials. The structural pipeline takes known crystal structures and systematically substitutes elements. What if this titanium oxide was made with zirconium instead, or hafnium, or combinations no one has tried? The compositional pipeline works in reverse. It starts with a chemical composition and predicts the most stable crystal structure from scratch. Together, these pipelines generated 2.2 million candidates. GNoME ranked them by predicted stability. The top 380,000 passed the threshold, and here's what's hidden in those 380,000 new materials. 528 new potential lithium-ion. These could enable solid-state batteries safer, faster charging, longer-lasting batteries that could finally make electric vehicles truly competitive with gasoline. 52,000 new layered compounds, materials structurally similar to graphene. Any one of these could become the foundation for next-generation electronics. And perhaps most remarkably, GNoME predicted stable structures that have no analog in nature, materials the universe itself has never produced. Not on Earth. Not on any known planet. Not in any star. Materials that exist only because an AI imagined them. When I understood this, really understood it, I had this moment where I thought, we're not just accelerating materials discovery, we're expanding what's possible. But discovering a material on a computer is one thing. Actually making it in the physical world, that's another challenge entirely. Unless you have a lab that runs itself. This is the A-Lab. The A stands for autonomous. Located at Lawrence Berkeley National Laboratory in California, the A-Lab is a fully autonomous robotic laboratory. Every instrument, every furnace, every characterization tool is connected to a central AI brain. That AI decides which materials to make, plans the synthesis recipe, directs robots to execute it, analyzes the results, and then based on success or failure adjusts its strategy and tries again. 24 hours a day, 7 days a week. No human supervision. Step 1. The AI selects a target material from databases of predicted structures, including those from GNoME, materials that have been predicted to be stable but have never been physically made by anyone, anywhere. Step 2. The AI determines the synthesis recipe, which precursor chemicals to combine, in what ratios, at what temperature. The AI evaluates thermodynamic data, published literature, and its own past attempts to choose the best approach. Step 3. Robotic arms take over. They select precursor powders from a chemical library. They weigh them with milligram precision. TA mix them, they press them they place the pellets into a high-temperature furnace. The furnace door closes. Temperature climbs. 200 grados, 500 grados, 800 grados, 100 degrees Celsius. Step 4. Wait. The furnace runs its program for hours. And while that material cooks, the lab isn't idle. Other robotic arms are synthesizing other materials simultaneously. Step 5. When the furnace cools, a robotic arm retrieves the sample and delivers it to an automated X-ray diffraction system. The XRD measures how X-rays scatter off the material, revealing its crystal structure, its atomic fingerprint. The AI compares the measured structure to the target. If they match, success. The predicted material now physically exists. If they don't match, the AI diagnoses what went wrong. Wrong temperature, incomplete reaction, impurities. It adjusts the parameters and tries again. And here's where it gets extraordinary. In its first published demonstration, the lab operated autonomously for 17 days. During that period, it targeted 58 materials predicted by AI materials that had never been made before by anyone. It successfully synthesized 41 of them. A 71% success rate. 41 materials that didn't exist 3 weeks earlier now exist. Let me give you a comparison that shows how significant this is. One PhD researcher might successfully synthesize one novel material in 6 to 18 months. The lab produced 41 in 17 days with 0 human researchers, and it worked through the night. Every night, while the world went about its business. 41 new pieces of physical reality quietly came into existence in a building in Berkeley, California. The lab was created under the leadership of Professor Gerbrand Cedar. His vision was simple but revolutionary. Close the loop. Don't just predict, make them, but both GNoME and the lab share a limitation. You still have to propose what to make. You're searching through possibilities, screening candidates. What if you could tell an AI exactly what properties you need and it would design a material from scratch? In January 2025, Microsoft showed this is possible. And if GNoME was an earthquake, Maturgen is the aftershock that permanently changes the landscape. GNoME is a screening tool. The iLab is a synthesis tool. Maturgen is a generative design tool. You tell it what you need, and it invents it. Think of it like DALL-E for images, but instead of pixels. Maturgen generates 3-dimensional atomic structures designed to meet your exact specifications. You tell Maturgen, I need a material that's thermally stable above 1,500 degrees Celsius, electrically conductive, and contains no rare earth elements. The underlying technology is a diffusion model. Instead of diffusing pixels, Maturgen diffuses atom positions and types in 3D space. During generation, it starts from pure noise atoms scattered randomly and gradually denoises them, like watching entropy reverse itself. Materials designed by Maturgen are 5 times more likely to be genuinely novel, and the property optimization is twice as effective. Microsoft researchers physically synthesized some of these designs. TA made 10, they tested them, the materials behaved as predicted. An aerospace engineer needs a material lighter than titanium, but stronger at high temperatures. Type it in. Maturgen designs it. A battery researcher needs a solid electrolyte that conducts lithium ions faster than anything currently known. Type it in. We've moved from the age of materials discovery to the age of materials design. We don't search anymore. We order. This isn't incremental progress. It's a fundamentally different relationship with the physical world. The implications are staggering. Let me show you 3 applications that crystallize why this matters. First, energy storage. GNoME identified 528 new lithium-ion conductors. Before this, the entire global research community had identified about 20 promising solid-state conductors. GNoME increased the candidate pool by 25-fold overnight. Solid-state batteries are considered the holy grail of energy storage. Replace the volatile liquid electrolyte with a solid material, and you get virtually no fire risk, faster charging, and longer lifespan. You also get higher energy density and performance at extreme temperatures. The bottleneck has always been finding the right solid electrolyte. You need fast lithium-ion conduction, stability across wide voltage ranges, no degradation over thousands of cycles, and scalable manufacturing. AI just generated 528 candidates to test. The timeline for solid-state batteries may have just accelerated by a decade. Second, aerospace. High-entropy alloys. These are alloys of 5 or more elements in roughly equal proportions. Traditional metallurgy rarely explored these because the combinatorial space is impossibly vast. 5 elements from the periodic table at varying ratios equals over 100 billion possible combinations. AI explores this effortlessly. Researchers using AI have identified high-entropy alloys with extraordinary property combinations. Think high strength and high ductility and corrosion resistance and thermal stability. Combinations previously thought mutually exclusive. For hypersonic vehicles traveling at Mach 5+, AI is designing ultra-high temperature ceramics. These ceramics withstand the 2000 degrees Celsius plus heating at those speeds, materials that would have taken decades to optimize traditionally. Third, carbon capture. AI is designing novel catalysts for direct air carbon capture materials that pull CO2 from the atmosphere. Today, direct air capture costs $400 to $600 per ton of CO2. AI-optimized catalysts could push that below $100 per ton, the threshold where carbon capture becomes economically viable at planetary scale. If successful, this single application could reshape climate strategy globally. These aren't distant possibilities. These are active research areas where AI-designed materials are being synthesized and tested right now. And we're just at the beginning. Here's what most people don't realize. This isn't just a scientific revolution, it's a geopolitical one. The nation that masters AI-driven materials discovery will control the physical technologies of the 21st century. The United States currently leads Google, DeepMind, Microsoft Research, Lawrence Berkeley Lab, multiple DARPA programs. The U.S. Department of Energy has made AI-accelerated materials a national priority. But China is investing aggressively. The Chinese Academy of Sciences runs autonomous materials labs. Chinese universities published over 40% of global research papers in 2023. China's Made in China 2025 strategy explicitly targets advanced materials as critical. China's dominance in battery manufacturing and rare earth processing gives it a massive head start in commercializing AI-discovered materials. Europe has Nomad and Battery 2030 Plus initiatives. Japan's National Institute for Materials Science is building AI platforms. South Korea's Samsung and LG are applying AI to displays and batteries. This is a global race, and whoever wins controls the materials. Whoever controls the materials controls the products. Whoever controls the products controls the industries. And whoever controls the industries controls the economy of the future.